On January 24th, 1986, a spacecraft did something that, to this day, no other machine built by our species has ever repeated. It flew past a planet tilted almost completely on its side, more than 7 billion miles from the Sun, and it found something so strange that scientists spent the next 38 years trying to figure out whether what they were looking at was even real. That spacecraft was Voyager 2, and what it found at that planet, and at the one after it, and then decades later in the empty dark beyond our solar system altogether, is a story about a machine that quietly did things its more famous twin never could, and that kept rewriting what we thought we understood about our own solar system almost every single time we looked closer at what it sent home. Here's the part most people do not know. Voyager 1 gets the headlines. It was first to interstellar space. It is the most distant human-made object in existence, and it carries the golden record everyone has heard of. But Voyager 1 only ever visited 2 planets, Jupiter, then Saturn, then a fast trajectory out of the solar system entirely, aimed to skip past Saturn's moon Titan and never look back. Voyager 2, launched 16 days earlier that same month in 1977, took a completely different path. Because of an alignment of the outer planets that happens only once every 175 years, engineers realized the second spacecraft could use the gravity of each giant planet to slingshot itself to the next one, and the next, and the next. Jupiter in 1979, Saturn in 1981. Then alone, with no twin alongside it anymore, it kept going to Uranus in 1986 and to Neptune in 1989. To this day, Voyager 2 remains the only spacecraft in human history to have ever visited either of those 2 planets. Not the only spacecraft that has visited them recently. The only spacecraft, period, in the entire history of our species that has ever gotten close enough to either ice giant to actually look. Even at the very first stop on the journey, before either spacecraft had done anything nobody expected, Voyager 2 was already doing something its twin physically could not do alone. When Voyager 1 passed Jupiter in March 1979, it discovered 9 active volcanoes erupting on the moon, Io, the first confirmed volcanic activity ever found anywhere beyond Earth. But a single flyby can only ever be a snapshot. It was Voyager 2, arriving 4 months later on its own separate trajectory, that checked back in on those same volcanoes and found 8 of the original 9 still erupting, giving scientists the first direct evidence that Io's volcanism was not a one-time event caught by chance, but an ongoing sustained process. Voyager 1, alone, could never have proven that. It needed its twin to come back and look again. And this was not luck. It was a deliberate, permanent trade-off baked into the mission before either spacecraft ever left the ground. Mission planners studied more than 10,000 possible trajectories before settling on the final plan, and the choice came down to one hard fork in the road. Voyager 1 was sent on a path specifically, engineered to fly close past Saturn's giant moon Titan, considered one of the most scientifically important targets in the entire outer solar system because of its thick, mysterious atmosphere. But reaching Titan the way scientists wanted meant bending Voyager 1's trajectory sharply out of the ecliptic plane, the flat disk in which the planets actually orbit the Sun, and once a spacecraft is bent out of that plane, there is no way back into it. The moment Voyager 1 completed its Titan flyby in November 1980, its planetary mission was permanently over, by design, before it had even happened. Voyager 2's path was built differently from day 1, specifically to preserve the option of continuing on to Uranus and Neptune if Voyager 1 succeeded at Titan first. It did. And so Voyager 2 quietly inherited a journey that its own twin was engineered, from the very beginning, never to be able to take. Uranus came first, and what Voyager 2 found there did not make sense. Just 11 hours before its closest approach, the spacecraft crossed into the planet's magnetosphere, the invisible magnetic envelope every planet with a working internal dynamo generates around itself. On Earth, that magnetic field behaves the way a bar magnet does, roughly aligned with the planet's rotational axis, centered near the planet's core. Every magnetic field human instruments had ever measured before Uranus followed something close to that same basic pattern. Uranus broke it completely. Voyager 2's instruments revealed that the planet's magnetic field was tilted a staggering 59 degrees away from its rotational axis, and the source of that field was not even centered inside the planet. It was offset by roughly a third of Uranus's entire radius, shifted off toward one pole. Nothing like it had ever been recorded at any other planet. And it got stranger from there. The region around Uranus appeared to be almost completely emptied of plasma, a vacuum where scientists expected charged particles to be present, paired with radiation belts so intense they were second in strength only to Jupiter's, the most powerful in the entire solar system. Scientists called it a contradiction they could not resolve. How could a magnetosphere be simultaneously stripped nearly bare of plasma and also home to some of the fiercest radiation ever measured? For 38 years, that contradiction sat there, unexplained, treated as simply one of the strangest, most fundamental facts we knew about an entire planet. That single flyby did not stop at the magnetic field. In the same encounter, Voyager 2 discovered 10 previously unknown moons around Uranus in one pass, including a small, heavily cratered world called Puck, and returned close-up images of the 5 large moons already known, revealing fractured, canyon-scarred surfaces that nobody had ever seen in any detail before. Moons like Miranda, whose jumbled patchwork terrain looked unlike anything else photographed anywhere else in the solar system. It found 2 entirely new rings circling the planet, and it measured the length of a Uranian day for the first time, 17 hours and 14 minutes, on a planet tipped completely on its side, tilted almost 98 degrees relative to its orbit, so that it does not spin like a top so much as roll along its path around the sun like a ball. Every one of those findings, the moons, the rings, the tilt, the day length, exists in our scientific record because of a single spacecraft, on a single pass that has never been repeated. Then in a study published in Nature Astronomy in late 2024, a team led by planetary scientist Jamie Jasinski at NASA's Jet Propulsion Laboratory went back through the data surrounding Voyager 2's approach and found something nobody had properly accounted for. In the days immediately before the spacecraft arrived at Uranus, the solar wind, the constant stream of charged particles blowing outward from the sun, had been unusually intense, compressing the planet's magnetosphere down to a fraction of its normal size. The researchers calculated that Voyager 2 likely encountered Uranus in a compressed, anomalous state that exists less than 5% of the time. In other words, the single closest look humanity has ever taken at this planet's magnetic environment may have caught it during one of the rarest windows possible. An unlucky snapshot mistaken for a permanent portrait. If Voyager 2 had arrived just a few days earlier, before that wave of solar activity hit, the solar wind pressure pushing against Uranus would have been roughly 20 times lower, and the entire magnetosphere the spacecraft measured could have looked fundamentally different. Nearly 4 decades of textbooks, models, and assumptions about one of our solar system's most mysterious planets may have been built on a single flyby that happened to catch it at the wrong moment. And there is still no way to fully verify it, because Voyager 2 remains the only spacecraft that has ever been there to check. A dedicated mission to Uranus, complete with an orbiter, has been proposed and studied, but as of now nothing has actually been approved or funded, which means the only real data we have about the planet's magnetic environment could remain for years or even decades longer, a single snapshot that scientists themselves now openly admit may have been taken at exactly the wrong moment. Then came Neptune in August 1989, the last planetary encounter of Voyager 2's entire 12-year journey, and once again, the only time in human history any spacecraft has visited it, passing within roughly 3,000 miles of the planet's cloud tops, closer to a planet than the spacecraft had come since leaving Earth 12 years earlier. Voyager 2 found winds tearing through Neptune's atmosphere at speeds exceeding 1,000 miles an hour, among the fastest ever recorded on any planet in the solar system. It photographed the Great Dark Spot, an enormous storm system roughly the size of Earth itself, a feature that had vanished entirely by the time Hubble looked for it years later, meaning it may have existed for only a handful of years total, ever in the entire observable history of that planet, and we happened to be watching at exactly the right moment to see it. It discovered rings around Neptune that had never been confirmed before, 6 new moons, and a magnetic field of its own tilted 47 degrees from the planet's rotational axis, and, just like at Uranus, significantly offset from the planet's actual center. 2 ice giants, 2 wildly tilted off-center magnetic fields, found by the same single spacecraft on the only 2 visits our species has ever made to either world. The rings themselves turned out to be strange in their own right, faint, dusty, and unevenly clumped in a way nobody had predicted from Earth-based observations, visible clearly in Voyager's images only because engineers used long exposure times and the backlighting of the sun itself to catch the fainter material. The spacecraft also photographed the moon Proteus, an oddly shaped body stretched almost as far into an ellipsoid as gravity will allow before an object collapses into a proper sphere, and it measured Neptune's auroras, the glowing lights, generated where charged particles slam into the upper atmosphere, finding them scattered strangely across wide regions of the planet rather than clustered neatly at the poles the way Earth's are, a direct consequence of that same wildly tilted off-center magnetic field. And then, 5 hours after its closest approach to Neptune itself, Voyager 2 passed within about 25,000 miles of the planet's largest moon, Triton, and found something that reshaped an entire branch of planetary science on the spot. Despite sitting at a surface temperature of roughly minus 391 degrees Fahrenheit, one of the coldest temperatures ever measured anywhere in the solar system, Triton was not simply a dead, frozen ball of ice the way scientists expected. Its surface showed almost no impact craters, meaning it had to be geologically young, recently remodeled by something. And in the images Voyager sent back, engineers spotted dark plumes rising several miles above the surface, active geysers, venting nitrogen gas, and dark dust particles high into Triton's thin atmosphere in real time as the spacecraft watched. It was only the second time in the history of space exploration that anything resembling active eruptions had been found on a world other than Earth, following Voyager's own discovery of erupting volcanoes on Jupiter's moon Io a decade earlier. Combined with an orbit that runs backward relative to Neptune's own rotation, a retrograde path unlike almost anything else of its size in the solar system, the data suggested Triton was not born alongside Neptune at all, but was instead a captured object. A wanderer from the distant icy Kuiper belt that Neptune's gravity had grabbed and pulled into permanent orbit millions of years ago. A single flyby, lasting only a handful of hours, rewrote our understanding of an entire class of outer solar system objects, and it has never been repeated since. Triton is now understood to be one of the best preserved examples of a Kuiper belt object we have ever directly examined up close, effectively a stand-in for the countless icy bodies drifting in that distant ring beyond Neptune's orbit that no spacecraft has ever visited individually, which means that, in a very real sense, the only close look humanity has ever taken at true Kuiper belt material came from a flyby of a moon, captured almost by accident during the final planetary encounter of a mission that was never designed to study that region of space at all. By the time Voyager 2 left Neptune behind, it had done something its twin, for all its fame, was simply never in a position to do. It had completed the only full grand tour of all 4 giant planets in the history of spaceflight. But the story does not end at the edge of the planets, because 30 years later, in the cold, dark well beyond the last planet, Voyager 2 did something its twin could not do a second time, and this one may end up mattering even more than everything that came before it. On November 5th, 2018, Voyager 2 crossed the heliopause, the outer edge of the Sun's protective bubble, and became only the second human-made object in history to reach interstellar space, following Voyager 1's crossing back in 2012. On the surface, that sounds like Voyager 2 simply repeating what its twin had already achieved. It was anything but a repeat, because Voyager 1's own plasma science experiment, the instrument specifically designed to directly measure the density, temperature, and flow of charged particles around the spacecraft, had failed decades earlier, forcing scientists to infer plasma conditions around Voyager 1 indirectly, through secondary measurements and careful modeling. Voyager 2's equivalent instrument was still working, still fully operational after 4 decades in space, which meant that when Voyager 2 crossed into interstellar space, it gave humanity something we had never actually had before, a direct, hard measurement of plasma on both sides of the boundary of our own solar system. Not an estimate, not an inference, an actual reading. And what that reading showed did something no one fully expected. Voyager 1's crossing back in 2012 had been messy, spread out over roughly 28 days, with the spacecraft detecting brief episodes where it seemed to still be connected to the solar wind even after appearing to have left it, a blurry back-and-forth transition. Voyager 2's crossing, 6 years later, was almost the opposite. Clean, sudden, complete in under a single day. Researchers publishing across 5 separate papers in the journal Nature Astronomy in November 2019 described the difference plainly, and also noted something stranger buried inside Voyager 2's data. Even after that clean exit, the spacecraft kept detecting particles that seemed to be leaking outward from inside the heliosphere, bleeding into the interstellar medium beyond a boundary that was supposed to be sharp and absolute. The edge of our solar system, it turned out, is not the crisp, clean lines so many textbook diagrams still show. It is porous. Then, in October 2020, a deeper analysis of the plasma density readings coming from both spacecraft together turned up something that genuinely surprised the scientists studying it. The plasma density kept increasing the farther Voyager 2 traveled beyond the heliopause, a pattern researchers had not predicted and could not immediately explain. They described it as evidence of a large-scale density gradient built into the structure of the very local interstellar medium itself, in the specific direction our entire solar system happens to be moving through the galaxy right now. A real physical feature of the space immediately outside our home that no model built before Voyager actually arrived there had ever anticipated. And because Voyager 1 exited the heliosphere from one location, in the northern hemisphere of that bubble, while Voyager 2 exited from a completely different location in the southern hemisphere, the fact that the 2 crossings looked so different from each other tells researchers that the heliosphere itself, the vast magnetic bubble that has shielded every living thing that has ever existed on Earth from the harsher radiation of the wider galaxy, is almost certainly not the simple symmetrical sphere it is so often drawn as. It may trail behind the solar system with a long tail, shaped less like a bubble and more like a comet, or possibly something closer to a croissant, asymmetrical in ways nobody has directly measured yet, because neither spacecraft has ever traveled through its wake side, and no other mission currently exists that ever will, not for decades. That density gradient finding matters for more than just academic curiosity, either. The sun moves through an 11-year cycle of rising and falling activity, and as it approaches another period of heightened activity, the shock waves it sends outward eventually reach the interstellar plasma surrounding both spacecraft, creating ripples that Voyager 2's still-functioning instruments can actually detect passing through, effectively letting scientists watch a wave move through a region of the galaxy no telescope on Earth has ever been able to observe directly in something close to real time. Every one of these discoveries, the impossible magnetic fields at 2 planets, no other spacecraft has ever reached. The geysers on a moon that shouldn't have had any activity left at all, the clean interstellar crossing that its twin could never have. Matched because its own instrument had already failed, came from a single machine that was only ever supposed to study Jupiter and Saturn and then go quiet. Instead, it kept finding things nobody expected at nearly every single stop along. A 49-year journey that has now carried it more than 13 billion miles from Earth, into the constellation Pavo, moving at more than 34,000 miles an hour, so far out that a radio signal now needs close to 20 hours just to make the one-way trip home. And it is still not entirely done. Its radioisotope power source loses about 4 watts every single year, permanently, with no way to reverse it. And mission engineers have already been forced to begin shutting down its instruments one at a time, including, in October 2024, the very plasma science instrument that made its clean interstellar crossing possible to measure in the first place, just to keep whatever is left of the spacecraft transmitting at all for a few more years. Engineers currently believe it may keep at least one instrument running into the early 2030s, though nobody can promise that with certainty on a machine this old. There is no way to send it more power. There is no way to send a repair crew. Every shutdown decision from here forward is final. Think about the shape of that story for a second. A spacecraft that was only ever guaranteed 2 stops, Jupiter and Saturn, ended up being the only human-made object to ever reach 2 entire planets, the only one to ever measure their impossible magnetic fields, the only one to ever catch a moon erupting with nitrogen geysers in real time, and the only one still capable, decades later, of directly measuring what the space between the stars is actually made of. None of that happened because Voyager 2 was luckier than its twin. It happened because it kept surviving long enough, stop after stop, decade after decade, to be in position when something worth seeing finally showed up. Voyager 1 will always be first to interstellar space, and first to be the most distant human object ever built. But almost every single thing on this list, the 2 planets nobody else has ever visited, the geysers, the clean read on the true edge of our solar system, belongs to Voyager 2 alone, and it always will, because nothing currently planned or funded will retrace this exact path again for decades, if ever. But for now, right now, it is still out there, still moving through the same dark that swallowed the great dark spot, still carrying data about places no other human instrument has ever reached. And there is still, for a little while longer, more it has to tell us. If this is the kind of story you want more of, subscribe and tell me in the comments which discovery in this one surprised you the most.